In our last video, we learned a little trick about linearizing a power function. Let's say you collect some data, you put your dependent variable on the x-axis, the y-axis, and your independent on the x, and let's say you get some function. We'll make it a negative power this time. The trick is this. If you take your original data, turn it into a log-log graph, and if you find that you get a straight line, doesn't matter if it's a positive slope or negative slope, if you find that you get a straight line, then you instantly know your variables have a power function. Like that. Not only do we instantly know the power function, but we can find the constants k and n using the slope of the log-log graph and the y-intercept of the log-log graph. Specifically, the constant k is equal to 10 raised to the power of the y-intercept from your log-log graph, and the constant n here, the power, equals m, the slope of your log-log graph. Slope of log-log graph. So that's a really cool trick, and it allows you to define or to discover the function between your variables. But the thing is, this only works, this log-log graph only works if you have a power function. What happens if you make your log-log graph and it's not a straight line, positive or negative? What happens then? Well, there is still something valuable. If a log-log graph doesn't linearize, that's the word we use, doesn't make a straight line, doesn't make a straight line, if it doesn't linearize your data, then you can conclude that you don't have a power function relating your variables, or a power function between your variables. Okay, so that's kind of helpful. I mean, sure, this is a nice thing to put into a lab report. It would be nice to show the log-log graph, then include some description. The log-log graph above clearly is not straight. Therefore, I can conclude I don't have a power function between my independent and dependent variables, whatever they are. That's a nice thing to put in a lab report. But what do you do next if this doesn't work, if the log-log graph isn't straight? Here's what you do next. So if you don't get a straight line from your log-log graph, what do you do next? You do a semilog graph. And we do a semilog graph, I'll tell you what that is, in order to test for an exponential function. So let's say you have some data. Let's see, what do? You roll some dice. You start with 100, and when the number of rolls n is 0, you have how many dice? I'll call it D, dice. You have 100. So this number would be 100. And you roll the dice, and you remove, after one roll, all of the 6s. So how many do you have after one roll when n is 1? Maybe you have, 86 or something. And you continue doing this experiment. With every roll, you remove the 6s, and then you count how many dice remain. So the graph you get, it's something like this, let's say. Right? It hits the y-axis, and it curves down. You might suspect negative exponential growth or a negative exponential function. But regardless, if your log-log graph doesn't work, the next thing you try is a semilog graph. A semilog graph is called semi because you only take the log of one axis. We are going to look at our column of d values, how many dice remain. Find that column of data, the column of numbers in Excel. Take the log, the natural log, ln, the log base e, of every one of those values, and plot those values on a new graph. Keep n as the x-axis. Don't change your x-axis. Well, if you get a positive line, positive straight line, then you have positive exponential growth. If you get a negative straight line, then you instantly know that you have negative exponential growth. So what does that mean? You know that the dependent variable is equal to some d sub 0 constant times e to the negative lambda I. Or for this particular experiment, what's our dependent variable? It's the number of dice that remain, which is equal to d sub 0 times e to the negative lambda, and the independent variable is how many rolls have we made, which is n. And here's the really cool part. If you add a linear trend line to your semilog graph, display the equation on the chart, y equals mx plus b. Okay, now I've actually done this experiment, and here's the equation that I saw when I put my data in, made a semilog graph, and added the line. I saw y equals negative 0.18x plus 4.7. Here's the really cool thing. The slope of my semilog graph, and what's the slope? The slope is this value, negative 0.18. The slope, actually it's the absolute value of slope, equals lambda, your decay constant. So in this case, the decay constant is 0.18. If you take E, Euler's number, and you raise it to the power of the y-intercept, that right there gives you d sub 0. So here's what I'm going to do. I'm going to take this equation, which I started, and I'm going to fill in lambda and d sub 0. And here's what I write down. D, the number of dice remaining, is equal to e to the power of the intercept, which is the y-intercept, which is 4.7, e to this power, right? That's the rule, times e to the negative, what's lambda? It's my slope, it's the absolute value of the slope, so lambda is 0.18, and my independent variable is n, number of rolls. And I can simplify, and I can erase e to the 4.7, and what do I get when I calculate e to the 4.7? So let's erase e to the 4.7, and I'm going to replace it with the value that I get, which is about 110 is the number. And so this here would be my exponential decay function. And it relates it tells me how does the number of dice remaining depend, or how does it vary as a function of the number of rolls, given the experimental setup that we take out all of the 6s every time we make a roll. Now, for units, if you were concerned with units, n is the value, n is how many rolls we've made. It's a counting number, so it has no units. Every counting number is unitless. This here, therefore, also has no units. Now, 110 is the number of dice I have before making any rolls. It's the starting value. I know what my starting value was. My starting value was actually 100. So 110 is pretty close. It's only about 10% off, from the true starting value. So this value d sub 0 gives you an idea of how good is your function. You can use this to evaluate how good is this function that you've just developed. And this function that I just circled in yellow is pretty good. It approximates my, it predicts my starting value within 10% of the true starting value. So what have we learned? We've learned that if a log-log graph doesn't linearize your data, doesn't make a straight line, you don't have a power function. The next thing to try is a semilog graph. So you can take your original data, turn it into a semilog graph using natural log of d, and if that makes a straight line, positive or negative slope, then you instantly know your variables, d and I, are related by an exponential function like that. And you also know that if you add the trend line and the equation to your semilog graph, and this, if you add the equation and trend line, then you can find your constants, d sub 0 and lambda. You can calculate the constants using d sub 0 is e to the power of the y-intercept on the semilog graph, semi-ln graph. And you can also use the fact that lambda, the decay constant, is the absolute value of the slope on the semilog or the semi-natural log graph, the absolute value. And that's what we've just learned in this video, where the intercept is b and the slope is m, whatever value Excel spits out.